I like to help you on a path from your idea and application to a sensor and a solution. Welcome to the channel and welcome to this video. If you're here, I'm assuming that you're looking for information about industrial sensors, what they are, how to pick them, how to choose the best one. Because there are so many sensors out there, it's a little bit overwhelming. Well, I'm sorry, but it's a lot overwhelming. So there's all the different types of sensors that are available just within the factory or logistics automation world. So I can understand it could be a little confusing. So I like to help you on a path from your idea and application to a sensor and a solution. And that's probably why you're here. You've got an idea of something you want to do, or you need something that can trigger another automation task. That's the first place to start. So the first question to ask yourself is, what is your goal? What are you trying to do? And we've got three questions. Number one, are you looking to detect something? That's where we're starting. That's really the basis of this video. Are you looking to detect the presence or maybe even a characteristic of a particular target? Detection is often used to trigger some other subsequent action, maybe reading a barcode, attaching a label to something, dimensioning a box, or maybe diverting something on a conveyor. But maybe you want to detect a particular color or different characteristic. So that's what we mean by detecting. So if all you need to do is just detect that something's there, you can skip the next two sections of measuring and positioning and get to the key families and part numbers for detection. So check out the chapters there. However, after you've detected your object, do you want to measure it? Number two, measuring. What's the size or shape of the object? What's the level of it in a hopper or silo? Or simply stated, how far is that target away from my sensor? Question number three, do you want to position? So after detection and measurement, do you need to know the location of the target for closed loop control? Maybe you want to do overfill protection or dry run protection, and you want to be able to control something, or maybe something on a conveyor or a crane. So knowing if you just need to detect or also measure and possibly position your target really sets the stage for what type of sensor and also what type of output you're going to look for in a sensor. So let's dive in here a little bit. Let's take a look at detecting. Let's dive into that further. So here we're looking at proximity of something. Is there something in my area? Is there something that I'm looking for within my range? Within that world, we have optical sensors, we have inductive sensors, we even have other sensors that can measure water and the capacitance of things as well. So with measuring now, we look at our measuring sensors. So what will your distance be to the target? And really, most importantly, how close can you get your sensor to the target? The closer you are, typically, the better your measurement is. Then, what type of precision are you looking for? Are you looking for microns, even nanometer measurements for maybe quality checks? Or are you looking for something that could potentially be a mile away, like maybe a crane? So we look at things from submicron all the way up to a mile. And then once you have that, one of the reasons to look at maybe something a mile away would be positioning, closed loop control, and feedback on the position of something. So for that, we often use long range distance measurement sensors. So we'll look here at these couple here, or using encoders, wire draw encoders, nonlinear encoders as well to track where something is along a conveyor or on a crane. All right, so now that you know what your goal is, let's take a look very specifically at one of the most common sensor types for detecting and measuring, and that would be photo eyes. So if we take a look at these operating principles, there's three main types of photoelectric sensors: through beam, retroreflective, and diffuse proximity sensors. So let's take a look at the first one, through beam sensors. So we have a sender and we have a receiver. Sometimes these are also called opposed mode sensors because they're opposed to each other. It's the most basic and most simple form, probably the least used these days. But you have a sender and you have a receiver. And when an object blocks the beam, you get an output. So through beam sensors, as well as retroreflective sensors, which we'll get to just in a little bit, are really just detecting a beam breakage like we have here. Is there something there or not there breaking the beam? There's no measuring. We don't know where it is within this space between these two. We just know I'm no longer getting light back, and I did get light back. So what are the benefits of a through beam sensor? They have a really long range. So we can get out to 330 feet, 100 meters with a whole lot of excess gain. They're great in outdoor applications and dusty, wet environments because of that extra gain. And we can also detect highly reflective targets. So even if your target is very shiny or curvy, something maybe like a vehicle or a shiny wrapper in a packaging application, or take it to the extreme, a mirror that reflects all the light away, the receiver still says, hey, I don't see any light coming from my sender. I'm going to give you an output, even if no light comes back at all. And we're going to contrast that to the diffuse proximity sensors that need that light from that target to come back. So it's a bit of a difference. The through beam sensors also can detect small objects because all they need to do is cover up enough of the receiver element to get that switching output. Well, what are some downsides? Well, typically they're more expensive. You've got double everything. So you've got the double hardware, the brackets, the setup, the cabling, the labor. So there's another option why they're more popular. We can look at retroreflective sensors. So with retroreflective sensors, we take the sender and the receiver and we put them in the same housing. Now, I'm calling them retroreflective sensors. Sometimes they're called reflex sensors or some other names for them. But what's required is a sensor of that type and some sort of reflector that is a very specific type of corner cube or diamond grade or retroreflector. It does a couple things. The light comes back and it actually gets polarized as well and changes the orientation of the polarization to block out other ambient light and reflected light back into it to reduce false trips from particularly optically difficult applications. So here again, like through beam, it's looking for just a beam blockage. Does it get the light back to it or not? Is there something blocking the reflector? So what's the benefits of using a reflector? Mounting for sure. So easy mounting. You've got one part with the sender and receiver in it, and then you have your reflector. You don't have to wire this or power this. You do have to mount it. And we can still get a lot of range, though. We're still looking at ranges up to 150 feet, 45 meters of range. So that's long enough for most applications. There's a simple adjustment mechanism, if it's even called that. Basically, you just have to physically align the sender and the reflector to make sure it gets the light. There's really no other adjustments or distance things to set up. We even have some special sensors that give a little bar graph on the back that even tell you how well you are set up and how well you are aligned on that reflector. Also gives you very safe detection of all objects, including shiny surfaces, including just the mirror. If no light comes back, it doesn't see the reflector and you still get an output. And we can also pick up transparent objects with very special retroreflective versions that look for a light drop going through a transparent object and then a light drop coming back, and it can pick that up and pick up completely clear materials. However, like the other ones, what are some considerations when looking at this retroreflective reflex technology? So they can have unreliable detection of small objects at long distances. So I'm sending my light out. If I'm a long way away, this entire reflector may be covered with light. And if I have a little item in here to try to pick up, the shadow caused by that target may not be enough to reduce the light enough to trigger the sensor. Also, lower quality retroreflective sensors may struggle with polarization effect of layers of, let's say, shrink wrap and may not be detected consistently. However, most modern sensors from reputable manufacturers have developed methods for dealing with this, and that really shouldn't be much of a concern, but certainly something that you'll want to check out in your application. Now we'll get to, I would say, the most popular type of sensor. So we have the diffuse proximity sensor. So the through beam and retroreflective, we're looking for a beam break. In this case, we're trying to measure that target. Sometimes these type of sensors that detect natural objects, meaning not a reflector, are also called diffuse reflective sensors because light is reflecting diffusely, meaning scattered. And that is as compared to a retroreflective sensor that is not scattering the light back. It's basically sending it back in the exact path it came from. So for the sake of clarity in this video, when I use reflective and reflectors and retroreflective, I'm specifically talking about sensors that use good quality triple reflectors or retroreflectors. Even diamond grade tape, reflective tape, will work well. So in the world of diffuse proximity sensors, there are three main types, with a hybrid interesting fourth type called foreground suppression, or FGS. But that's outside the scope of this current video right now, so check the channel later for more videos on that interesting topic. So let's start with the most basic and least expensive, but also least popular type, energetic sensors. This type of sensor emits light and evaluates the amount of light that's reflected back to the receiver element, which makes it very impacted by the color of the target. It makes it impacted by background lights. So something in the background, like a light from a fork truck or a reflective vest, can trigger it because enough light gets back, it triggers the threshold and the sensor goes off. So if the application, though, if your application doesn't have a changing background and background lights and all that, because let's say inside of a machine, then this might be a great and cost-effective solution. However, if there is optically noisy backgrounds or no backgrounds or inconsistent background, we don't know where the light is back there, then that background ought to be suppressed by, well, a background suppression sensor or a sensor in background suppression mode, and sometimes we'll call that BGS mode, background suppression. So a background suppression sensor not only evaluates the amount of light coming back from a target like the energetic sensor, but also the position of the object. Using a sort of triangulation based on the distance to the target, the reflected light is focused on a CMOS or other segmented receiver array. In this way, the sensor can be taught to only activate if there's a target closer than the taught-in distance, ignoring even more intense light coming from further away. Then another option is time-of-flight sensors. Now, time-of-flight sensors don't really even measure the distance, like background suppression sensors do using triangulation. This animation shows how the sensor measures a round-trip time of a laser bolt, but the same is done with ultrasonic pulse or even a radar pulse as well. The time for the bolt of energy to exit the sensor, hit the target, and return is measured based on the speed of light or sound at the ambient temperature or radar wave propagation time. The distance is determined. So if we focus on light and photoelectric sensors, which makes up the majority of diffuse proximity sensors in the automation market, we need to be aware of reflectivity. How much light is reflected and returned to the sensor to be evaluated? When you look at data sheets, you will see terms like 90%, 18%, 6%. So if you'd like a short detour into the world of physics and how all this came about, you can check out the link here. I'll put in the description and hopefully up on screen. It's where white balance stuff came from. This is a lot of photography and other things are involved here. But what's important to know for this is that 90% refers to white target and a 6% refers to a black target. And then there's an array of things in between. Now, I doubt you know exactly the reflective nature and number for your target. So to make life easy, most quality manufacturers of sensors give you a best and worst case specs for the detection range. So we'll tell you what it is, a 6% black target and a 90% white target that's giving back more light. Also, most background suppression sensors also give you a characteristic curve for how far away a 6% target needs to be from a really bright 90% background. So check out the whole thing about characteristic curves in a separate video that I'll link to in the description as well, because that's very important to look at, is how far away from a bright target do you need to be. So let's take a look at what some of the benefits are and considerations as well. So first off, on these diffuse proximity sensors, you don't need a reflector, you don't need a receiver element, much easier to install and set up. You only have one side. Objects in the background won't be detected, particularly with background suppression sensors. And we get repeatable detection of small objects. So now we're not looking at light and a shadow on a big reflector. We're really just looking for getting light back from that small target. And detection of dark objects, black objects in front of a white or shiny background, Those range in quality and value from the manufacturers. So a more expensive sensor will do a better job than a lower cost sensor, even from the same manufacturer. So those characteristic curves are very interesting to take a look at, and as well as testing to see how well they work in your application. Considerations to keep in mind when looking at these. Well, triangulation operating distance is limited. The CMOS receiver in these sensors, they're only so big. So the range and the span is limited. Anytime we're over maybe a meter, we'll go to time of flight. Less than a meter, we're probably looking at a lot of the triangulation sensors. And typically, the larger the sensing range is, the less precision you will get, particularly with triangulation sensors. The smaller the measurement span, though, the higher the precision, and even getting down into nanometer levels with triangulation sensors. Now, if we take a look at time of flight sensors, they're a good choice when the target is further away. But the target needs to be at least 4 inches away, but they function extremely well out to hundreds of meters. These sensors are slightly more expensive, though, than your standard sensors because of the additional optics and technology going on than we just have in the retroreflective sensors. So the next step here, can I help you get to maybe a family of sensors, maybe even to a part number to start looking at? So for optical proximity sensors, I really suggest starting with the W10 family. It's very easy to use, and especially if you're really new to this. It has a touch screen display on it, and it cycles you through all the options you can have. And it makes it very easy to set up and use the sensor. You don't need a manual. And there's videos that help through that as well. You can do all sorts of great things with this sensor. If you need something a little bit more challenging, an application that's more challenging, maybe look at the W4 or the W16 family, and I'll put some information in the description there. But if you simply need a through beam or retroreflective beam break sensor, then something in the H18 family is the way to go. Retroreflective version and proximity version. So there'll be some additional sensor information and I'll put in the descriptions as well, and key part numbers depending on what you're looking for, maybe the longer range or something. And if your object you need to detect is metal and you can get within about 50 millimeters, then I think an inductive sensor is really the way to go, particularly in harsher applications where optical sensors may have some challenges. So for this, I would suggest starting with the IMX sensor, and we give a part number here as well. There's lots of different outputs types. There's lots of different sizes. So if I had to guess on one, I would pick a 12 millimeter barrel housing because it's kind of right in the middle. And I think that would be the best place to start. Now, if you're looking for something else, not just if something's there or not there, you're looking maybe for color marks or contrast marks on printing applications, or even luminescent tracers that manufacturers put in on shrink wrap and other plastic and glues that you optically can't see, but the luminescence can pick it up, then there's a bunch of sensors here, which again, I'll put in the descriptions, and particularly starting with the CSS, high resolution color sensor, can pick up color marks, contrast marks, do a great job. These are some really great choices for detection. If you're looking to detect and measure, I'm really a DT80 fan. So let's take a look at the DT80 for measurement. It also detects, because you can't measure it unless you detect it. So this sensor gives you switching outputs, just like the other photo eyes, but you also can get analog and IO link actual distance values out to potentially up to 80 meters. So a lot of settings in here. We can be really fast and not as precise, or can be super precise but not as fast. So those are some really cool things you can do inside the sensor. There's only one part number, the DT80, and it can detect and measure the distance to just about anything. Just like photo eyes, you can get a switching output for detecting an object, but you can also get analog and IO link distance values as well. If your target is something that an optical laser like the DT80 might not be able to pick up, we might need to change wavelengths, and specifically into a ultrasonic sensor like the UC40 would be a great place to start. It has a customizable sound cone, really great range, and can see transparent materials, including water. And if you want something with more precision for applications like quality control and inspection, take a look at our OD family line. So the OD 200, 2000, there's a 5000, some other ones, 7000. You can get to sub-micron and even nanometer resolutions. On the other side of that range spectrum, though, if you're looking to measure and detect and potentially position a target that is really far away, like 150 meters or even 1.5 kilometers, almost a mile away, then we are looking at a DL100 or DL1000 family. Now, once you've detected your target and you know where it is, encoders help track the subsequent movement of the target, particularly on conveyors and cranes. So to choose a good starting point for encoders, the first choice is decide if you need an absolute or an incremental encoder. Then the next is what kind of output you need and how best does it mount to your equipment. And to learn more about encoder types and how to narrow down options, check out videos in the Industrial Sensor YouTube channel we'll have a link to, and it helps walk through how to make those choices for an encoder. So thank you for coming to the channel and watching this video. I hope I was able to help you and assist you take yourself from an idea and an application all the way down to a family and a part number. If you found this video helpful and you're looking for answers to some of your questions, remember, you're not alone here. There's a lot of people in exactly your same boat, exactly your same condition. So put some questions down in the comment section. Like and subscribe too. That helps people find it when you're searching. But let's get a chat going. Ask some questions. Take a look at other people's questions and answers, and let's contribute in this area. If this is helpful, check out other videos that we've put in this channel to look at all sorts of different sensors and how-tos and unboxing and ways to help you choose the right sensor and to be able to understand them and use them. Thanks for being here. Appreciate it. See you next time.